I think at the end of what we did last time is we looked at 3 operations. Okay, we looked at, on this figure, we looked at the rotate left operation, and we went through a little code walkthrough of how that's implemented. And the key issue, or the key point here about the rotate left operation, is that the black height of the tree and the order of the tree are maintained. Okay, so you understand that by doing a rotate left, the black height is not affected, because the number of black links from the parent all the way through to any one of these subtrees is unchanged. Is everybody clear on that? Because you only count the black links, so the number of black links is not affected. That's a key, that's an invariant of this, so that's a key idea. And then we saw the how to implement that. And then here we saw that there's also a rotate right operation, and it just undoes what the rotate left operation does. It does it in the opposite order. And here again, the black height and the order are maintained for this, and this was a programming exercise for you. And then we also saw this flip colors operation, where the colors of the link of the parent link coming into the node, and then the colors of the left child and the right child are all flipped. And here again, now this is provided that H arrow left and H arrow right are both red to begin with. Okay, providing that they're both red to begin with. Then if you flip the colors, then the black height is unchanged in any path that goes through this, from the parent up to any one of the subtrees. Is everybody clear on that? How that works, how that keeps that. Now, so those ideas are crucial. So now look, you guys, and so flip colors, that's that code, some of that code is left for you to do. If you just do rotate right and flip colors, I think that code is sufficient to do the insertion. You could actually program that up now, and insertion should work. There's only one more that you need to do that's required, and that's the min func method, but that's only required for deletion. So anyway. So now we're going to learn how to insert into an Llrb tree. Now this is really very slick. So let's take a look at the code for insert. Now, watch this. The first method that we have is the tree version of insert, right? And what does it do? It does root gets root arrow insert underscore root comma data. So here the tree version of insert just does what? Calls the node version. Yeah, of insert. Are you with me? And then after it does all of its stuff, then root arrow color gets black. Oh, I think now that I'm going through this, we went through this at the end of class last time, right? Right. And so the node version of insert does what? It's recursive. It does if h equals null pointer. So then what it does, it returns new node with data. And we saw that new calls the constructor, and the constructor makes what kind of a link to the parent for the parent?
Red link.
Red. And now why is that? Why does it do that? Because if you insert a node with a red parent, that does not alter the black height. So the black height property stays the same. Is everybody with me on that idea? Okay. And because that's a return right away, we don't need an else. Are you with me on that? Notice that code style. You see, if it returns, it doesn't do fix up either. So now what happens is if data is less than h arrow underscore data, so here we are in a node and we compare it with the h arrow underscore data, and if data is less than that, then now look, it's h arrow left gets. Are you with me? So what is h arrow left get? It gets a insert h arrow left comma data. All right. So H arrow left is used twice. It's H arrow left gets something, and then insert H arrow left actually returns a pointer that H arrow left gets. All right, and similarly with H arrow right. And if we found a duplicate, we just don't do anything. All we do is return fix-up. Now what we want to do is learn how fix-up works. Now this is so slick. And so here is the reason, or here is the idea behind the design of fix-up. Now look, you guys, what I have listed here are all the attributes of a left-leaning red-black tree. And what are they? A red-black tree is a binary search tree. Every link is either red or black. Every child that is an empty tree is a leaf with a black link to its parent. No path from the root to any link has 2 red links in a row. All paths from each node to all of its leaves have the same number of black links. And then a little aside here, a left-leaning red-black tree is a red-black tree. And then because of that, every red link is to a left child. Now I ask you, if you insert a new node as a leaf at the bottom of a red-black tree and its parent link is red, have you violated, and we do it according to the way that code did, left, right, left, right. Have you violated the first property? Or is the resulting red-black tree still a what? A binary search tree. Is it? Yes, because of the way because we did it in order, right, left, and then put it as a leaf. Question?
Did the last part of the insert make it black, the parent?
That was only the root of the whole tree.
Oh, okay.
Yeah. So we agree that property is not violated. How about every link is either red or black? Is that property violated? No, because we didn't put a purple one in, right? So it's either red or, that's still good. Every child that is an empty tree is a leaf with a black link to its parent. So that one that we stuck in, didn't the constructor make it null pointer and null pointer? So aren't they? And so is that still satisfied? Okay. No path from the root to any leaf has 2 red links in a row.
We don't.
That should be true.
No path from a root to any leaf has 2 red links in a row.
I feel like you don't know. I think it might.
Ah, you are right. It might be violated. Why? How could that happen?
It just depends on where it was.
Yeah, and how could it? And how would that? How could you have 2 red links in a row? Now you know it's a left-leaning red-black tree, right? So how could that happen? So like if the tree is like this, and there's a
red.
Ah, yes, that's what I was trying to think of. Yeah. So if this is nil, and this is nil, and this is an actual value, and then we have a node here. Yeah. So this is how it could be violated, right? So what could happen is if we come here and we come here and it gets put here, and then its parent is red, then that could be violated. All right. How about the next one? So all paths from each node to all its leaves have the same number of black links. What about that?
It's fine.
I think that's fine because when we inserted this, if you insert a red one, it doesn't count. So that one's fine. And how about every red link is to a left child?
Maybe.
Every red link is to a left child. What about that one?
It might not.
It might not be. How could that happen? This could be nil. This could be nil. And if you add it, you might be adding it. It might be needed to be added here. So what have we concluded here? What have we concluded by this analysis? These 2 ones are the only ones that might be violated. Now, is everybody clear on that? No path from the root to any leaf has 2 red links in a row. That might be violated. And furthermore, every red link is to a left child. That might be violated. Now, does everybody see? So do you understand then that all the other ones are good? It's a search tree. The black heights are all maintained. Okay. The only thing are these 2. So what does that mean? What that means is that the purpose of fix-up is to correct 2 possible problems. And so we have to understand what those problems are so we can understand how fix-up works. First of all, the additional red link might be to a right child. Okay? And the additional red link might produce 2 red links in a row. Now, is everybody clear on that? So those are the 2 problems that we have to solve on fix-up. So watch how this works then. Fix-up H makes 3 adjustments, and by making these 3 adjustments, it fixes up those 2 problems. So check this out. It does these 3 things, and by the way, it does these 3 things with 3 if statements, and the if statements are sequential. They're not nested. It's one if statement followed by another if statement followed by another if statement. It's 3 simple if statements, each one followed by one simple little operation. So check this out. First, if the red link is a right link, it makes it a left link. So in other words, if it got here, if it got inserted here, if the new node got inserted here, so now that this is nil, and this is nil, so now it looks like this. The first piece of code in fixup.h makes this red link a left link. All right? Now, in the second one, if there are 2 red left links in a row, then, okay, so that's the other condition that it has to handle. So if there are 2 red that's hard to say fast. She sells seashells by the seashore. If there are 2 red left links in a row, rotate right in preparation for the last adjustment. Now this is kind of an interesting thing. What it does is when it sees 2 red ones in a row, it rotates it right. But now, if you have 2 reds in a row, can you visualize this? We'll see a slide, but can you visualize? If you have 2 red links in a row, they're both left links, right? If you rotate right, what's going to happen? You're going to have 2 neighbors. Yeah, you're going to have a left and a right, both being red. But then, what's the third operation? Yeah, and if the left and right links are both red, flip colors. So you see, they're done. These corrections are done in this order. Are you with me? These corrections are done in this order, and it might be that that you do the second one in order to take advantage of the third one. Okay. So now here's the code. Look how easy this fix-up is. So here's the precondition. H arrow left and H arrow right are roots of left-leaning red-black trees. So here's the thing, you guys. This fix-up is going to fix up the tree on the way back, not just at the bottom. Because what it's going to do is, by fixing it up at the bottom, it might propagate a what? It might propagate a red link. You know when you do flip colors? It might propagate a red link up. And so that means the same thing that we're doing at the bottom, we're going to have to do what? Up one level. And then that's going to do a fix up. And then what will that do? That might propagate a red link up. So we'll fix up another level, and we'll fix up another level. Now, does everybody see how that works? How the calling sequence works? Okay? Because look, you guys, let's go back to, that was fix up. Let's go back to the code for insert. Do you see the very last thing in the code for insert is what? return fix up H. So what happens is, on the way down, it's calling if data is less than H arrow data, so it goes to the left. And then at that point, it starts over again. And then it does if it's right, boom, and then it goes there, and then it starts over again. And then it starts over again. And all the way down, it has all its little what? All those little local H's that are the parameters are pointing to those nodes. Do you see what we're saying? And then the very last thing that happens is, so the one at the very bottom does what? It does return fix up.h. After it fixes it up and it returns that, then what does it return to? The one that called it, the next one up. But then what does it do? It returns fix up.h. So it fixes it up. And then it fixes it up and it fixes it up and it fixes it up all the way up. Now, you got to understand that calling sequence. You see how clever that is? It's really neat. It's recursive, and you have to understand that on the way down, you have to understand how recursion works and how how it calls, and then once it makes the call, it interrupts it and starts, and then that gets interrupted, that gets interrupted, that gets interrupted. But now the very last thing is return fix up. So he returns fix up, and then it fixes it up, and then the other one will call its fix up, and the other one will call its fix up, and on the way up. So we go all the way down to insert, and we fix up all of our problems on the way back. It's kind of like we litter on the way to the party, and then we sweep our stuff, crumbs up on the way home or something. I don't know. Yeah, you see. Yeah, question?
Is there a time when black height would have to be incremented by 1?
No. Well, yes. Well, obviously, yeah, let me answer that again. So, yeah, good question. Is there a time when the black height would ever have to be incremented by 1? The answer is absolutely, it has to, because we start with a tree with the black height, yeah. So, yes, and not only that, but when we remove, it's going to have to be decremented.
Does that happen in the main function, or is?
It happens automatically. As long as we maintain that the black height is, as long as our invariants are correct, it happens automatically. You see, and we can see when we trace through the code how it changes. Okay. So let's go back to the code for fix up, knowing that that's how the calling sequence works. All right. So check this out, you guys. Here's the first one. So here's our fix up code. If is read H arrow right. Are you with me? So look, here we are. Here's H. Here's H. And what we are saying is, if is read H arrow right. Now, actually, somebody asked the other day, how do we know the link? Because the link is stored in the parent link is what's stored here. So if I'm here, how do I know this link is read? Well, here's how you do it. You just test H arrow right color. You see how that works? Okay? So here it says, if is read H arrow right, what? H gets what? Rotate left. And now, do you remember what rotate left did? What did it do? It brings this up. It brings that red one down. And it puts the P here and the H is here. But what does it return? It returns the what? It returns the P. Well, no, in the code it returned the P, but now this H gets that P. So this is pointing to the root of the rotated tree. Now, is everybody clear on that? You see how that code works? Okay? So if is read H arrow right, H gets rotate left. Now check this out. How do we know if there's two reds in a row? If what? Is read what? H arrow left and H arrow left. So what is that? So what's that situation? That situation is what? I've got, actually I shouldn't be drawing all this stuff because I got slides coming up, but All right, so you can see if there are two rights in a row, then what does it do? Rotate right, in preparation for what? And now if is read what?
Flip.
H arrow left and H arrow right. That means we got two siblings, each one with red links to the parent, to the common parent. Do what? Flip. And every single one of these maintains the what? We saw that every single one of these operations maintains the what? The black height. Yeah. Are you with me? So the black height, it won't change. Actually, how will the black height change? When that red, see, because if you have two reds here and they flip, and so the parent, the one that was coming down, turns from black to red, eventually that red could do what? Propagate up to the what?
Oh, to the base.
To the root of the tree. But then we said, what did the root of the tree do? Turn it to black. So there's the change in the black height. Okay, so that all happens at the end. Okay, so check this out. So now I have, here's an illustration of these three operations. So the first one is inserting as a right leaf with a black sibling. Okay. So here we go. Check this out. So let's suppose that we have our initial tree. H is pointing to 50, and by the way, this is at the base of, this is at the bottom, like at the bottom of a left-leaning red-black tree. And so let's suppose that H is pointing to the 50, and the left is nil and the right is nil, and so H is a pointer to the node that for which we're going to do an insertion. And now let's suppose that we insert 60. So what, oh, and by the way, one more thing. That line that's going up from 50, the reason it's going straight up, what that means is that could be either coming from the left, or, I mean, it could be, 50 could either be a left child or a right child. Either way. So when we have one come up, that means that's a signal for, that's, the interpretation of that is that 50 could either be a left child or a right child.
Or it could be the root.
Or it could be the root. Good point. Okay? And so now, and so if we insert 60, we come down from to 50. 60 is bigger than 50, and now the right side of 50 is nil. So we insert the 60, right? And so now which code comes into play? That first one. And so what does that do? Rotate left. And so we rotate left, and boom, that was a fix-up. Are we good? You see how that worked? Okay. And now what about the second one? How about we insert a leaf? How about inserting as a left leaf with a red parent? So let's suppose our initial tree has, and this could be a subtree, okay, is 90, and then it has left child 70, and then we have nil, nil, and nil. So you understand now that in coming from the 90, if we go to the left, what's the black height? What's the black height at 90? It's 1. And notice that the number of black links from 90 all the way to each one of those nils is 1. So the black height, so you see this does satisfy the property of being a red-black tree before we do the insert. Maybe we should double check the other one. You understand that before we added anything, we just had 50 and nil and nil. The black height of 50 is what? 1. Are you with me? And it's still, the black height is still 1 after we do.
Does the root have a color? I mean, I put this in notes. It has a color.
The answer is yes. Because it is a node and it has a color. And if you notice that when we did the demo, when we started off with an empty tree, it was black. And even when we did all those insertions, it always wound up being black. So there is like an imaginary parent of the root doesn't have a parent. So this fictitious parent of the root, the link to that is black. Okay, but anyway, so let's come down. Let's come back to here. So inserting as a left leaf as a left leaf with a red parent. So what could happen is, if we insert 60, what's going to happen? 60 is less than 90, 60 is less than 70, and then, so where is 60 going to be inserted? It's going to be inserted here. Now, in the insertion, you know, when the pointer was at H, and then when we call it with nil, what did it return? It returned a pointer to the new one. Are you with me? Look, this part of the code right here on the insertion. Here you see the very first part of insert. If H equals null pointer, do what? Return what? New node T data, and it doesn't do fix up. It just returns. So do you see then that this picture, part B of this picture, inserting as a left leaf with a red parent, do you see then that H is pointing to the 70 when it does its fix up? Now, is everybody clear on that? And the H, the other H that's pointing to 90 was the H on the way down, the call chain. Now, does everybody see how that, what the setup is? Okay. So that's insert. So there's the insert 60. Now watch what happens. Now what happened if it was what was the code now? I should have two screens here. What is it? If is read H arrow right. Now what happens there? If is read H arrow right is H is the 70, pointing to the 70. What about the is read H arrow right? Is it? No, it's black. It goes to that black. It's the black link to the nil. So that one doesn't execute. That if does not execute. Are you with me? And then, all right. So do you see at this point, H is pointing to the 70, and we have two reds in a row, but we are at H after the insertion. Okay, what was the first one? Okay, so H is at 70. Now, what was the first criterion?
H arrow right.
H arrow right red. It's not.
Right.
Now, what's the second one? If H arrow left and H arrow left is red, but that's not, because the first one is red from 70 to 60, but the one from 60 to the left nil is not. So that's not. And now what about the third one? Left and right, are they red? And they're not. So the fix-up doesn't do anything. It just returns. But what does it return to? Look, it returns, so there's no fix-up. And so now it goes to the next level up. But now in the next level up, what happens? It does those same three things. So now so what is the first thing it checks? If the right is red, it's not. If the what? If the left is red and the left of the left is, but now they are. Okay? So now what? So now what happens? Rotate right. Okay? But we're still up there at H, and now what was the third one?
Left.
Now the left and right. So now what does it do? It flips the colors. Phew.
There we go.
Yeah. Now, does everybody see that sequence? Yeah? So that's inserting as a so that's inserting as a left leaf with a red parent. Now, here's an interesting phenomenon that can happen. It's possible in some circumstances, and it does happen, that this curious thing where it does something and then it undoes it. But that's just the way it is. The code is nice and clean and simple, but this little phenomenon that we're going to see can actually happen. So let's suppose our initial tree is a 50 as the root, and then a 40, a red link to a 40, so that's a left link with the 40. And we are going to insert as a right leaf with a red sibling. So if we insert 60, where's the 60 going to go? To the right of 50. Are you with me? So here in part B, we insert the 60. Yeah? Are you with me? And because we inserted the 60, the H that's doing the test for the fix-up is the one at 50. That's the first one. Are you with me? Now, what were those tests? I think we know the test now. The right, but now what is the right red?
Yes.
Ah, so look what it does. And now what was the second test?
If the left is left,
If the left is red and the left of the left is red. But now it what?
it is.
It is. So it actually, the code actually does this. It does it and it undoes it at the same level. You see what I'm saying? Because it's in preparation for the third. And now what was the third?
Swap the left and right.
Left and right, then, yeah, then flip. Okay, so boom. And now what's happening? Now look what's happening. What's happening? What's going up? A what?
A red.
Now look, you guys, a red is being propagated up. But look, don't you see? That's exactly the same situation as if we did a what? Inserted a red at that point. Do you see? Because it's the red that's getting propagated up, we can just fix that up the same way we fix this up, because all those properties are true. That, you know, those two criterion, you know, it could be messed up in one of two ways. It could be propagating up as a right child, or it could be propagating up as two reds in a row. But as long as we just do fix up on the way up the same way so now, once we did fix up at one level, we know that the left-leaning red-black trees are correct below us. Right. And so we fix it up on the way up, and it could get propagated all the way up to the root of the tree and then be turned to black. Right. Yeah? Does everybody see how that works? Very clever. So that was an example of just at one level with an insert. So here's how it could work. In fact, I think we did this. I think we were surprised at this feature when we did the demo. Let's suppose that we have an initial tree like this. So we have 20 and then 10 on the left and then 40 and 30. So that's our initial tree. And we have gone down H, you know, we have an H at the root, we have at 20, we have an H at 40. And so now what happens is, let's suppose that what number are we inserting, did we say? We're going to insert 50, right? So now where is the 50 going to go?
To the right of 40.
It's going to go to the right of 40. And it's going to be inserted as a what?
A red.
As a red. So here, 50 is going to be inserted at 40 as a red. So this is a result of H arrow right gets insert, H arrow right comma data. Right? But now fix up happens. Now, can you tell what's going to happen here? Now that we know the story, the first one is what? Test for what? A right child. So what's it going to do? It's going to rotate it left like this. But now what's it going to do? It's going to left, and so it's going to actually undo that and go here. But now what's it going to do? It's going to left and right, so it's going to what? Flip and go up. So now what's that going to make happen? Look, what's that going to make happen?
A right.
That's going to make a red be what?
A red be red.
A right one red. But that's all right, because we're calling fix up. See, so it's as if we were inserting a red. You see, when the red propagates up, it's the same thing as when we added the red at the bottom. All right. So now what does this do? It rotates left. Okay. And then what? Checks to see if what? Left of left is red, but it's not. But then what? Left is red and right is red, but that's not. So boom, there we are. Now I tell you, this code that Sedgwick has done here, those I'll tell you right now, those three cases for fix up, in a general red-black tree, there are 6 cases just for the insertion. And it was hairy. This is, and I can tell we're catching on here really quickly. Those 3 things, I mean, we can understand how those work. And the neat thing about it is that it's the exact same fix-up for insertion is the fix-up that we use for deletion. So here, let's think about how deletion is going to work. I'll give you previews of coming attraction. We won't do any code, but let me just give you some ideas. So how do we delete from an Llrb tree? Now watch this. here is an outline of how deletion is going to work. First of all, what you do is you find the node to remove, right? And how do you find the node to remove? Left, right, left. That's a search tree. Boom, you find it, right? Then, now, do you remember with our dictionary how we did remove? With our binary tree dictionary, do you remember how we did what we did? We found the what? The what of the what? We found the what? The maximum of the left child, which was the predecessor node. Are you with me? And then we copied the data up, and then we did what? Remroot. Are you with me? But look, the way we do it with this one, it's the same idea, only instead of finding the maximum of the left child, which is the predecessor, we find the what? Right. Instead we find the minimum of the right child, which is the successor. And that works equally well. In fact, it works. We have to do it this way. There's a slick little thing here coming up. Right? So you find the minimum of the right child node to remove, which is the successor node, and then we use this little technique of just copying the data, and then we remove the minimum of the right child. But look, it gets better, because what did we have to do with our binary search tree dictionary? We had to do remroot because we were guaranteed that the what? That the right child was empty, but we had to pull the left child up. But look at here. Here's a useful fact. The minimum of an Llrb tree has what? Has what as a left child? Okay, so you know, here we have a tree. Now, if this were just a regular tree, where would be the minimum? It would be this one, right? So we know because it's a minimum, the minimum has nil as a left child, right? But look, because this is a left-leaning tree, we know what? What do we know?
That is not right.
We know the right child cannot be red because the tree is left-leaning. But if the right child can't be red, that means what? It's got to be black. But if it's black, that won't work, because then this doesn't have a unique black height. So we know that there is no, we don't have to do remroot. We only have to do what? Just delete. There's nothing down there. This minimum is all by itself. So put that in your pipe and smoke it. All right. So what we'll do now. So what we're going to do the next class is we're going to go through the code for delete, and it's slightly more complicated than insert. But anyway, we've got insert under our belt now, so we'll be good. And I think this project is not due until Tuesday, right?
Correct.
But you can, like I say, you can code it up now and it'll get it to work. No problem. All right. See you next time.
Great. That was cool.
Well, I mean, is that test true or false?
False.
It's false, so it doesn't do anything. Look, do you see what we're saying here? That is, at part B, after it has done the, wait, shoot. I'm leading us down the wrong path again. Darn. I'm going to have to cut it. Man, this is going to be a short video.